Imagine space not as a void, but as a sea of invisible forces.
Whether it is the rush of air over a wing, the pull of a magnetic field, or the transmission of a digital signal, we describe these forces as vector fields.
To the untrained eye, these fields look like a chaotic tangle of arrows, but hidden within that chaos is a profound, dual nature. The Great Splitter, Helmholtz decomposition, D1 and D5. The central pillar of our story is a concept known as the Helmholtz decomposition. Think of it as a master prism that takes a single messy field and splits it into two distinct personalities. This isn't just a mathematical trick. It reflects how the universe actually works. This decomposition ensures energy orthogonality, the idea that these two parts of the field can coexist without interfering with each other's energy. They are independent, like two different instruments playing in a single orchestra. The two personalities, D2 and D4. When we look through our prism, the field separates into two fundamental types of motion. 1. The irrotational field, the straight shooter, as seen in D2 and detailed in D4. These fields are curl-free. They behave like water flowing perfectly straight out of a tap or gravity pulling an object directly toward the Earth. They move from a source to a sink without ever spinning or looping. Because they are so direct, they can be described by a simple potential, a single value at every point that tells the field where to go. 2. The solenoidal field, the swirler. These fields are the opposite. They are divergence-free, meaning they never truly start or end, they only loop. Think of the swirling water in a whirlpool or the magnetic loops around a bar magnet. They don't expand or shrink. They simply rotate. The interaction and the problem. The core problem we face is calculating the total interaction, or integral, of one of these fields, the curl-free straight shooter, within a specific 3D volume. Because this field is so well behaved, we expect the calculation to be elegant. We assume that the field flows in a way that respects the geometry of the space it occupies. The boundary constraint, D3. However, the beauty of this theory depends entirely on its environment. This is where the boundary condition comes in. For our two field types to remain perfectly independent and orthogonal, they must interact with the walls of their container in a specific way. As shown in D3, if the field leaks through the boundary or hits the wall at an incorrect angle, the independence is lost. The calculation becomes messy because the irrotational and solenoidal parts start to overlap and interfere with one another. To find our solution, we must ensure the field is anchored to the surface of the volume, effectively neutralizing the spin and focusing only on the direct flow. The conclusion: from volume to surface. By understanding that our field is curl-free and properly contained by its boundaries, we reach a stunning conclusion. Instead of having to measure every single point inside a complex 3D space, we only need to look at what is happening on the surface. The internal complexity vanishes, replaced by a boundary simplicity. We find that the total energy of the field is defined not by the chaos within, but by how the underlying potential rests against the edges of its world. This transformation allows scientists in fields as diverse as electromagnetism and fluid dynamics to solve massive problems by simply looking at the skin of the system.